Somewhere in the infinite darkness between galaxies, beyond the reach of our most powerful telescopes, beyond the edge of everything we can see or touch or comprehend, lies a question that could redefine existence itself. It whispers through the equations of theoretical physics like wind through empty corridors, challenging every assumption we hold about reality, time, and our place in the cosmic order. What if everything we know, every star that burns in the night sky, every planet that orbits in silent majesty, every thought that has ever formed in a conscious mind exists not as the totality of reality, but as a single note in an infinite symphony we cannot hear? What if our universe, with its billions of galaxies and its 13.8 billion-year history, is nothing more than a bubble floating in an ocean so vast that our entire cosmos appears as insignificant as a grain of sand on an endless shore? This is the story of humanity's most profound discovery, that we may be children of something unimaginably greater than ourselves. The cosmic womb. In the deepest silence of space, where no sound has ever traveled and no light has ever touched, lies a truth so profound it could shatter every assumption we hold about existence itself. 13.8 billion years ago, in a moment that defies comprehension, everything that would ever be, every star, every planet, every thought, every dream, emerged from a singularity smaller than the period at the end of this sentence. But what if that moment of creation was not the beginning, but rather a birth? What if our universe, with its 100 billion galaxies and its infinite complexity, emerged not from nothing, but from within something far greater and more mysterious than we have ever dared to imagine? The question haunts the corridors of theoretical physics like a whisper in an empty cathedral. For decades, scientists have accepted that the Big Bang marked the absolute beginning of time and space itself. Yet now, as we peer deeper into the cosmic microwave background and measure the universe's accelerating expansion with unprecedented precision, we are confronted with data that suggests something impossible, that our universe may be nothing more than a bubble, floating within an infinite ocean of reality we cannot see, cannot touch, and cannot comprehend. If true, this revelation would transform us from cosmic protagonists into cosmic children, born not of void, but of something unimaginably vast and ancient. The implications reach beyond physics into the very core of what it means to exist, to think, to dream in a universe that may itself be dreaming within another. The discovery of cosmic horizons. The story begins not with a single eureka moment, but with the gradual accumulation of cosmic mysteries that refuse to conform to humanity's expectations. In the winter of 1929, Edwin Hubble stood in the frigid dome of the Mount Wilson Observatory, his eye pressed to the eyepiece of the 100-inch telescope that would forever change our understanding of existence. Through that lens, he witnessed something that contradicted everything astronomers believed about the cosmos. The universe was not the static, eternal stage that Einstein had envisioned, but a dynamic, expanding theater where every galaxy rushed away from every other with speeds that increased with distance. This observation planted the first seed of a revolutionary idea that would grow to encompass the entirety of cosmic history. If the universe was expanding now, uniformly and predictably, then it must have been smaller in the past, ultimately collapsing backward through time to a singular point of origin where all of space, time, and matter compressed into a mathematical impossibility. Hubble's discovery was humanity's first glimpse into the possibility that the universe had a beginning, that existence itself had a birthday. The mathematical framework for this cosmic birth came from unexpected quarters. Alexander Friedmann, a Russian mathematician working in the chaos of post-revolutionary Russia, had solved Einstein's field equations and discovered that the universe could not be static. It must either expand or contract. His work, initially dismissed by Einstein himself, described a cosmos that breathed with the rhythm of expansion and contraction, a universe that could emerge from nothing and potentially return to nothing. Georges Lemaitre, a Belgian priest and physicist, took Friedmann's mathematics further, proposing what he called the primeval atom, a cosmic egg that contained all of existence in a state so compressed and energetic that the laws of physics themselves would break down. This primeval atom would explode outward in what British astronomer Fred Hoyle mockingly called the Big Bang, a name that stuck despite its creator's skepticism. But mathematics and observation remained separate realms until 1965, when two radio astronomers at Bell Laboratories made a discovery that would validate the most audacious theory in the history of science. Arno Penzias and Robert Wilson were attempting to calibrate a sensitive radio antenna when they encountered a persistent background noise that seemed to come from everywhere at once. No matter which direction they pointed their instrument, no matter what time of day or night they observed, the signal remained constant, a faint whisper of radiation that filled all of space. This cosmic microwave background radiation was exactly what theorists had predicted. The afterglow of creation itself, the stretched and cooled remnant of the primordial fireball that gave birth to everything. The universe had revealed its baby picture, a snapshot taken when it was only 380,000 years old and still glowing with the heat of its violent birth. In that ancient light, cosmologists could read the history of everything that had ever been or ever would be. Yet, even as this triumph validated the Big Bang theory, it raised questions that seemed to multiply like fractals, each answer revealing deeper mysteries. The cosmic microwave background was remarkably uniform, varying by only 1 part in 100,000 across the entire sky. This uniformity suggested that regions of space, now separated by billions of light years, had somehow been in thermal equilibrium in the early universe, despite the fact that light could never have traveled between them in the time since the Big Bang began. The discovery of cosmic expansion and the cosmic microwave background had opened a door to the past, but beyond that door lay puzzles that would challenge the very foundations of physical law. The universe was not simply expanding, it was expanding with a precision that seemed to require impossible fine-tuning, a cosmic conspiracy that demanded explanation. Hidden within the triumph of Big Bang cosmology were clues that would eventually suggest something far stranger than anyone had imagined, that our universe might not be alone. The paradox of perfection. As instruments grew more sophisticated and measurements achieved ever greater precision, cosmologists began to encounter a series of profound puzzles that seemed to violate the basic principles of how the universe should behave. Each discovery, rather than clarifying the picture of cosmic evolution, instead revealed new layers of mystery that threatened to undermine the entire framework of modern cosmology. The first paradox emerged from the very uniformity that had made the cosmic microwave background so beautiful and confirming. Opposite sides of the observable universe, regions separated by distances so vast that light could never have traveled between them since the moment of creation, somehow maintained nearly identical temperatures. This was the horizon problem. How could regions that had never been in causal contact achieve such remarkable thermal equilibrium? It was like discovering that two sealed rooms on opposite sides of the Earth, with no connection between them and no shared history, had mysteriously maintained exactly the same temperature for millions of years. The laws of thermodynamics demanded that isolated systems should evolve toward different equilibrium states, yet the universe displayed a coordination that seemed to require some form of communication or shared origin that standard Big Bang theory could not provide. Even more disturbing was the flatness problem, a puzzle that struck at the heart of cosmic geometry itself. Einstein's general relativity revealed that space could curve in 3 possible ways. It could be closed like the surface of a sphere, open like a saddle, or perfectly flat like an infinite plane. Observations suggested that our universe was balanced precisely on the knife's edge between these possibilities, with a geometry so close to perfect flatness that it defied explanation. The mathematics were unforgiving. If the initial density of the universe had differed by even 1 part in 10^60 from its observed value, cosmic evolution would have followed a catastrophically different path. A universe slightly denser would have collapsed back into a big crunch within microseconds, never allowing time for atoms, stars, or galaxies to form. A universe slightly less dense would have expanded so rapidly that matter could never have clumped together to create the cosmic structures we observe today. This level of fine-tuning was like balancing a pencil on its point for 13 billion years, not just improbable, but seemingly impossible without some underlying mechanism that standard cosmology could not explain. The universe appeared to have been crafted with a precision that suggested either impossible luck or the operation of some deeper principle that physicists had yet to discover. Most troubling of all was the monopole problem, a puzzle that emerged from the marriage of cosmology and particle physics. The extreme temperatures and energies that characterized the earliest moments of the universe should have created exotic particles called magnetic monopoles in vast quantities. These theoretical particles, possessing only a north or south magnetic pole instead of both, were predicted by grand unified theories that attempted to merge the electromagnetic, weak, and strong nuclear forces. Yet despite intensive searches using the most sensitive detectors available, not a single magnetic monopole had ever been observed. It was as if the universe had been carefully cleaned of these primordial relics before galaxies, stars, and life could emerge. The absence of monopoles suggested that something dramatic had occurred in the early universe, some process that had diluted or eliminated these exotic particles while preserving the conditions necessary for the complex evolution that followed. These three paradoxes, horizon, flatness, and monopole, pointed toward a shocking possibility that would revolutionize cosmology. They suggested that the Big Bang, far from being the absolute beginning of everything, might have been preceded by something else, a process or event that could explain the universe's seemingly impossible perfection. The standard model of cosmology, which had seemed so elegant and complete, was beginning to crack under the weight of its own success. Each new observation, rather than confirming the simple picture of cosmic evolution, instead revealed evidence of fine-tuning so precise that it seemed to demand a designer, or at least a mechanism far more sophisticated than the straightforward expansion from a singular beginning that Big Bang theory described. Cosmologists found themselves confronting a universe that was not simply expanding, but expanding with a perfection that seemed to violate the principles of probability and thermodynamics. Something had shaped the early universe with extraordinary care, setting initial conditions so precisely calibrated that billions of years later, complexity and consciousness could emerge from the cosmic dance of matter and energy. The inflationary revelation. In the winter of 1979, a young physicist named Alan Guth was struggling with the monopole problem when he stumbled upon an idea that would revolutionize humanity's understanding of cosmic origins. Working late in his office at Stanford, surrounded by blackboards covered with equations, Guth was exploring the possibility that the early universe had undergone a phase transition, a sudden change in the properties of space itself, similar to water freezing into ice, but far more dramatic and consequential. What he discovered in those calculations would transform cosmology forever. If a hypothetical field, later called the inflaton field, had dominated the energy density of the very early universe, it could have driven a period of exponential expansion so violent and rapid that it defied every intuition about how space and time should behave. In less than a trillionth of a trillionth of a trillionth of a second, a region smaller than a proton would have inflated to the size of a basketball, carrying with it all the matter and energy that would eventually become our observable universe. This process, which Guth named cosmic inflation, offered elegant solutions to all three major paradoxes that had plagued Big Bang cosmology. The horizon problem dissolved. Regions that appeared to have never been in causal contact had actually been in intimate thermal equilibrium before inflation stretched them beyond each other's horizons. The universe's apparent fine-tuning became inevitable. Inflation would naturally drive any initial curvature toward perfect flatness, regardless of the geometry with which space began. The monopole problem vanished. Any exotic relics from the pre-inflationary epoch would have been diluted to undetectable levels by the exponential expansion. But as Guth worked to refine his theory with colleagues including Andre Linde, Paul Steinhardt, and Andreas Albrecht, they discovered implications that reached far beyond solving the problems of standard cosmology. The same quantum fields that drove inflation would not have behaved uniformly across all of space. Instead, quantum fluctuations, the fundamental uncertainty that governs behavior at the smallest scales, would have caused inflation to end at different times in different regions. This realization led to a profound and unsettling conclusion. Inflation might not be a one-time event that occurred once in the distant past, but an eternal process that continues indefinitely. While inflation ended in our region of space 13.8 billion years ago, allowing the Big Bang to proceed and our universe to evolve, it would have continued in other regions, creating the space and conditions for entirely separate Big Bangs to occur. Andre Linde developed this concept into what he called eternal inflation, a model in which new universes are constantly being born from the quantum fluctuations of an ever-inflating background. Each region that exits inflation becomes the seed of a new universe, complete with its own Big Bang, its own evolution, and its own potential for complexity and life. Meanwhile, the surrounding space continues to inflate exponentially, creating room for even more universes to nucleate and develop. The implications were staggering. Our universe, which had seemed to encompass everything that could possibly exist, was suddenly reduced to a single bubble in an infinite foam of cosmic creation. We were not alone, not even close to alone. Somewhere beyond our cosmic horizon, separated by distances that could never be crossed and times that could never be synchronized, other universes were experiencing their own versions of cosmic evolution. Some might be similar to ours, with familiar particles and forces. Others might operate under entirely different physical laws, with different fundamental constants and different possibilities for structure formation. The mathematics of eternal inflation painted a picture of reality so vast that it challenged human comprehension. If our observable universe contains roughly 10 or 80 atoms, then the number of other universes in the eternally inflating multiverse would be truly infinite, not just very large, but actually without bound. Every possible variation, every conceivable alternative history, every imaginable configuration of matter and energy would not only be possible but inevitable somewhere in the endless expanse of the multiverse. This revelation transformed the very meaning of existence. We were no longer the product of a unique cosmic event, but one realization among infinite others of the creative potential inherent in the laws of physics. Our universe was not special in its existence, but perhaps only in our ability to observe and contemplate it. We had become cosmic democrats, citizens of a multiverse where every possibility was explored and every potential was realized. Yet, perhaps most unsettling was the realization that eternal inflation, if correct, meant that new universes were being born at every moment. The process that had created our cosmos was still occurring, somewhere beyond the reach of our instruments, generating new realities faster than we could count them, each carrying within it the potential for its own forms of complexity, consciousness, and wonder. The architecture of the impossible. As the full implications of eternal inflation began to permeate the scientific community, physicists realized they were confronting something far stranger and more profound than anyone had initially imagined. The multiverse was not simply a larger version of our universe, but a fundamentally different kind of reality, where the very concepts of beginning and end, inside and outside, cause and effect, would need to be completely reconsidered. String theory, the leading candidate for a unified theory of quantum gravity, suggested that the multiverse might be even more exotic than inflation alone could explain. In string theory's mathematical landscape, the fundamental forces and particles that govern reality emerge from the vibrations of tiny, multidimensional strings existing in a space with as many as 11 dimensions. The specific way these strings vibrate and the particular configuration of the extra dimensions they inhabit determines the physical laws that operate in any given region of the multiverse. Leonard Susskind and other string theorists calculated that there could be as many as 10⁵00 different possible configurations, different vacua in the language of physics, each giving rise to a universe with its own unique set of physical constants and fundamental forces. Our universe, with its specific values for the strength of gravity, the mass of the electron, and the speed of light, would represent just one point in this vast landscape of possibilities, no more special or fundamental than any other. This realization transformed the fine-tuning problems that had long puzzled cosmologists. The apparent precision with which physical constants seemed calibrated for the existence of complexity and life was no longer mysterious. It was inevitable. In a multiverse containing 10⁵ different universes, some would naturally possess the conditions necessary for stars, planets, and biology to emerge. We observe the universe we do not because it was specially designed, but because we could not exist in the vast majority of alternatives where the constants fell outside the narrow range compatible with complexity. But the architecture of the multiverse revealed even more disturbing possibilities. If eternal inflation was correct, then the process of universe creation was not only ongoing but accelerating. Each new universe that formed would itself undergo inflation, creating space for even more universes to nucleate. The result would be a fractal structure of cosmic creation, with universes budding from universes in an endless hierarchy of birth and growth that stretched beyond any finite description. The scale became incomprehensible. Our observable universe, vast as it appears to us, would be infinitesimally small compared to the totality of our own universe, which would itself be infinitesimally small compared to the multiverse as a whole. We were not just cosmically insignificant, we were embedded within layers of insignificance that stretched beyond the power of mathematics to fully capture. Perhaps most unsettling was the suggestion that consciousness itself might play a role in determining which universe we experience. The anthropic principle, the observation that we find ourselves in a universe compatible with our existence, began to take on new and troubling dimensions when combined with certain interpretations of quantum mechanics. Some physicists proposed that the act of observation might actually select which branch of the multiverse becomes real for the observer, making consciousness not just a product of cosmic evolution, but an active participant in determining the structure of reality. Hugh Everett's many worlds interpretation of quantum mechanics suggested that every quantum measurement splits reality into multiple branches, with each possible outcome occurring in a separate universe. Combined with the multiverse of eternal inflation, this created a picture of reality where not only every possible universe exists, but every possible history within each universe is simultaneously real. Every decision ever made, every path not taken, every alternative outcome would be realized somewhere in the infinite expanse of existence. The implications reached beyond physics into the deepest questions of philosophy, meaning, and identity. If every possible version of ourselves exists across the multiverse, if every choice we make is simultaneously made and not made in other realities, then what meaning can we assign to our particular experience? Are we unique individuals, or simply one instance among infinite others of the same pattern of consciousness? Time itself became problematic in this context. If new universes were constantly being born, each with its own timeline and causal structure, then the very notion of simultaneity across the multiverse lost meaning. There was no universal now, no cosmic clock that could synchronize the experiences of conscious beings across different bubble universes. We existed not just in space, but in our own local time, separated from other realities by barriers that could never be crossed. The theoretical landscape. The scientific community found itself navigating an unprecedented diversity of theoretical frameworks, each offering its own vision of how universe birth might actually occur and what it might mean for the nature of reality itself. These models, while sharing common mathematical foundations, painted dramatically different pictures of the cosmic process that had potentially given rise to everything we know. Alan Guth's original chaotic inflation proposed that quantum fluctuations in a primordial scalar field could spontaneously trigger the explosive expansion that creates universes. In this model, the pre-inflationary state resembled a false vacuum, a seemingly stable condition that was actually metastable, capable of tunneling to a lower energy state and releasing enormous amounts of energy in the process. Like bubbles forming in superheated water, new universes would constantly nucleate from the quantum foam, each carrying away a portion of space-time to develop independently according to its own physical laws. André Linde's eternal inflation painted an even more dynamic picture. In his framework, inflation never truly ends globally, but continues indefinitely in most regions of space, with occasional pockets exiting the inflationary phase to become what we recognize as Big Bang universes. Each exit event creates a new bubble universe, while the surrounding space continues to inflate exponentially, creating room for even more universes to form. The result resembles a cosmic reproductive system, with parent regions giving birth to daughter universes in an endless hierarchy of creation. String theorists develop their own unique perspective on multiverse cosmology. In their models, the fundamental forces and particles emerge from the vibrational modes of one-dimensional strings existing in a higher dimensional space. The specific configuration of these extra dimensions, how they curl up and connect to each other, determines the physical laws that operate in any given region. Transitions between different configurations could occur through quantum tunneling events, with each transition potentially giving birth to a new universe with entirely different physics. Perhaps most intriguingly, string theory suggested that our universe might be embedded within a higher dimensional structure called a brane, short for membrane. Just as a two-dimensional surface can exist within three-dimensional space, our three-dimensional universe might exist on a four-dimensional brane floating in an even higher dimensional space. Other branes, containing their own universes with their own physics, might exist parallel to ours, separated by distances measured in extra dimensions we cannot perceive. The ekpyrotic model, developed by Paul Steinhardt and Neil Turok, proposed a radically different mechanism for universe creation. Instead of emerging from inflation, our Big Bang might have resulted from the collision between two branes in higher dimensional space. This collision would have released enormous amounts of energy, creating the hot, dense conditions we associate with the early universe. The model suggested that such collisions might be periodic, with universes being born, evolving, and eventually colliding again in an endless cycle of cosmic death and rebirth. Even more speculative was the work of cosmologists like Sean Carroll and Jennifer Chen, who explored the possibility that our universe might have emerged through quantum tunneling from a previous universe that had reached a state of maximum entropy, heat death. In their model, random quantum fluctuations could occasionally create pockets of low entropy within the thermal equilibrium of a dead universe, regions where time could begin anew and complexity could once again emerge from simplicity. Our Big Bang, in this view, was not a beginning, but a resurrection, a phoenix rising from the thermal ashes of an earlier cosmos. The implications of black hole cosmology added yet another layer of exotic possibility. Building on Stephen Hawking's work on black hole thermodynamics, some theorists propose that black holes might serve as wombs for universe creation. As a black hole forms and evolves, it might give birth to a new universe through processes occurring at the event horizon or within the mysterious singularity at its center. This universe would be causally disconnected from our own, existing in a separate region of spacetime that could never be directly observed or accessed. Lee Smolin developed this idea into his theory of cosmological natural selection, proposing that universes with physical constants that favor black hole formation would produce more daughter universes, leading to a kind of evolutionary process that would naturally select for cosmologies capable of generating complexity. In this model, our universe's apparent fine-tuning for complexity and life would be explained by its evolutionary history. We exist in a universe whose physical constants were shaped by eons of cosmic reproduction and selection. Each of these theoretical frameworks carried profound implications for understanding our place in the cosmic order. They suggested that the reality we inhabit might be far stranger and more interconnected than we had ever imagined, part of a vast network of cosmic creativity that stretches across dimensions and scales we are only beginning to comprehend. Instruments of discovery. The search for evidence of our universe's potential cosmic parentage has pushed scientific instrumentation to the very limits of technological possibility, requiring measurements of extraordinary precision and sensitivity to detect the subtle signatures that might reveal our multiverse heritage. The Planck satellite, launched by the European Space Agency in 2009, represented humanity's most sophisticated attempt to decode the cosmic microwave background radiation, the afterglow of our universe's birth. Operating at temperatures just 0.1 degrees above absolute zero, Planck's instruments mapped variations in the ancient radiation with unprecedented precision, measuring temperature differences as small as 1 part in a million across the entire sky. Within this cosmic baby picture, cosmologists searched for specific patterns that might betray interactions with other universes. If our bubble universe had collided with another during the early phases of cosmic evolution, the impact should have left circular or elliptical patterns in the microwave background, cosmic bruises that would provide direct evidence of our multiverse context. Planck's data revealed intriguing anomalies: a large cold spot in the southern sky, unexpected alignments in the temperature fluctuations, and other features that did not match the predictions of the simplest inflationary models. Ground-based telescopes like the Atacama Large Millimeter Array in Chile's Atacama Desert represent another frontier in the search for multiverse signatures. ALMA's network of 66 radio antennas, operating in perfect synchronization at an altitude of 16,000 feet, can detect the faint polarization patterns in the cosmic microwave background that might carry information about gravitational waves generated during inflation. These primordial gravitational waves would represent ripples in space-time itself, carrying information about the conditions that existed before our universe's Big Bang. The Large Hadron Collider at CERN approaches the question from a completely different angle, using the highest energy particle collisions ever created in a laboratory to probe the fundamental structure of reality. By accelerating protons to 99.999% the speed of light and smashing them together, the LHC recreates conditions that existed microseconds after our universe's birth, potentially revealing new particles or forces that might be signatures of extra dimensions or hidden symmetries predicted by multiverse theories. Particularly intriguing is the search for evidence of supersymmetry, a theoretical symmetry that predicts the existence of a partner particle for every known particle in the Standard Model. The discovery of supersymmetric particles would provide strong support for string theory and its prediction of a vast landscape of possible universes. Similarly, the detection of extra dimensions, which might manifest as violations of the inverse square law of gravity at very small scales, would revolutionize our understanding of space-time and our place within it. The detection of gravitational waves by LIGO and Virgo has opened an entirely new window into the cosmos, one that might eventually reveal signatures of cosmic inflation or even interactions between different universes. Advanced LIGO's laser interferometers can detect changes in distance smaller than 1/10,000th the width of a proton, making them sensitive enough to observe the stretching and compression of space-time caused by passing gravitational waves. Future space-based gravitational wave observatories like the Laser Interferometer Space Antenna, LISA, will extend this capability far beyond what ground-based detectors can achieve. With arms millions of kilometers long, LISA will be sensitive to gravitational waves generated by the most violent events in cosmic history, potentially including the process of cosmic inflation itself or the merger of entire universes. The search for dark matter, which comprises roughly 27% of our universe's mass energy budget, has taken on new urgency in light of multiverse theories. Deep underground detectors, buried in mines and laboratories around the world, search for the collision signatures of hypothetical dark matter particles. Some multiverse models suggest that dark matter might actually consist of ordinary matter from parallel branes or shadow universes, gravitationally influencing our reality while remaining otherwise invisible. Perhaps most ambitiously, some physicists have proposed methods for directly detecting other universes through quantum entanglement effects. If particles in our universe remain quantum entangled with particles in other universes, a possibility suggested by some interpretations of eternal inflation, then measurements performed in our universe might reveal correlated changes in apparently random quantum events, providing direct evidence of multiverse connections. The James Webb Space Telescope, with its unprecedented infrared vision, is searching for anomalies in the most distant galaxies that might reveal signatures of pre-Big Bang physics or interactions with other universes. By observing light that has traveled for over 13 billion years, Webb can peer back to within a few hundred million years of our universe's birth, potentially revealing evidence of the cosmic conditions that preceded inflation. Future proposals for even more ambitious instruments continue to push the boundaries of what might be possible. Arrays of quantum sensors in space, networks of atomic clocks with unprecedented precision, and detector systems that might be sensitive to the quantum foam itself all represent potential pathways toward direct observation of multiverse phenomena. Children of the infinite. We stand at the threshold of a revelation that fundamentally alters humanity's place in the cosmic order. If our universe was indeed born inside another, if we are children of an infinite hierarchy of cosmic creativity, then every assumption about meaning, purpose, and significance must be reconsidered through the lens of ultimate perspective. The implications stretch far beyond physics into the deepest questions of philosophy and consciousness. In a multiverse of infinite possibilities, every moment of joy and sorrow, every act of creation and destruction, every thought and dream that has ever formed in a conscious mind exists not once but countless times across the vast expanse of reality. We are simultaneously unique and utterly common, precious beyond measure and infinitely replaceable. Our choices matter infinitely because they define our immediate experience, and yet they matter not at all because every possible choice is being made somewhere in the endless tapestry of existence. This paradox of significance reveals something profound about the nature of consciousness itself. If our universe emerged from another through the process of cosmic inflation, carrying within it the potential for complexity, life, and awareness, then we are not accidental byproducts of cosmic evolution, but integral participants in an infinite process of self-discovery that stretches across dimensions we can barely imagine. We are the universe's way of understanding itself, its method of experiencing wonder, its technique for transforming the abstract mathematics of existence into the lived poetry of consciousness. The ancient question, why is there something rather than nothing, transforms completely in light of this possibility. There is something rather than nothing because nothingness is impossible in a reality where existence itself is infinitely creative, where the laws of physics naturally generate new universes with the same inevitability that stars generate light. We exist because existence explores every possibility, and consciousness exists because even an infinite multiverse requires observers to give it meaning, to collapse the quantum superposition of all possible realities into the specific experience of being alive and aware. Yet, uncertainty remains our constant companion on this cosmic journey. The same instruments and theories that suggest our multiverse heritage also remind us of the fundamental limits of observation and knowledge. We may never know with absolute certainty whether we are truly children of another universe, or whether our cosmos stands alone in an empty void. The very nature of inflation and universe birth might place permanent barriers between us and direct knowledge of our cosmic context. This epistemic humility carries its own form of beauty and meaning. If we are indeed embedded within infinite layers of reality, then our highest calling is not to conquer or control, but to observe, to understand, to appreciate the magnificent complexity of which we are part. We are cosmic archaeologists, sifting through the evidence of our own origins with the same wonder and dedication that we bring to understanding the evolution of stars, the formation of galaxies, and the emergence of life from non-living matter. The story of our potential cosmic birth reminds us that every sunset observed from Earth, every embrace shared between conscious beings, every moment of understanding achieved through scientific discovery represents something precious and irreplaceable, even, perhaps especially, in an infinite multiverse. We are not diminished by our cosmic context, but elevated by it, not lost in immensity, but found within it, not separated from the whole, but eternally connected to it through bonds that stretch across dimensions of space and time we are only beginning to comprehend. In the end, whether our universe was born inside another matters less than how we choose to live within the reality we have been given. The same quantum fields that might have driven our cosmic inflation also gave rise to the chemistry that made life possible, the physics that allowed complexity to emerge, and the neurology that enables consciousness to contemplate its own existence. We are made of universe stuff contemplating universe stuff, cosmic children wondering about our cosmic parents, finite beings grappling with infinite possibilities. The multiverse, if it exists, does not diminish the importance of our particular experience, but rather contextualizes it within a framework of ultimate creativity and possibility. We are conscious beings in a cosmos that may itself be conscious on scales we cannot comprehend, observers in a universe that observes itself through our eyes. Children of mystery, raising questions that echo through infinite halls of existence we may never fully explore but will never cease to wonder about. This is the profound gift of scientific discovery. Not certainty, but ever deeper appreciation for the mystery of existence itself. Whether we are alone in a single universe or part of an infinite multiverse, whether we emerged from nothing or from something unimaginably vast, we remain conscious participants in the cosmic story, witnesses to beauty and complexity that exists regardless of the ultimate nature of reality's foundations. In our questions about cosmic parentage, we discover something essential about the nature of consciousness itself, that to be aware is to be part of the universe's own process of self-discovery. To be alive is to participate in the cosmic conversation between possibility and actuality, between the mathematical and the experiential, between the infinite and the intimate. We are, in the deepest sense, the universe coming to know itself, one thought, one moment, one wonder at a time.